wave function and properties. The particle in a classical mechanics is a wave packet in quantum mechanics, right? And this wave packet consists of waves of different wavelength lambda. So where the particle is present, all this wavelength will constructively interfere, and all other region it will interfere destructively. Okay, so here the particle can be found in between this distance, that is we call delta x, and in each position there is a probability density for the particle to be found there. We can say the particle will be here, but we can say the probability of finding the particle at this position is this much, and probability of finding the particle at this position is this much. So the wave nature of particle is represented by wave function psi, and the probability of finding the particle in various location is phi star. That is probability density rho, or we represent by mod phi square. So this one is the probability density. That is the probability of finding a particle at any location. Okay, now we are going to discuss about the properties. First property, the wave function psi must be finite. That is, psi must be a converging function. What is it meaning? As the distance x is going to plus or minus infinity, what happen? Psi must be tends to 0. See, you can see, suppose this is our x-axis. So at this position there is phi. But when we are going to infinity, there will be phi equal to 0. There will not be any wave function corresponds to this particle. So the wave function is limited to a certain region, that is delta x region, and beyond that region the wave function should be 0. Second one, psi must be square integrable. That is, if we are integrating the probability density from minus infinity to infinity, it should be a finite value. Why? Because if we are getting infinity means the particle is spread over minus infinity to plus infinity. Then how we can say it is a particle? We know particle is a localized. It is localized to certain region only, that is delta x region only. So the wave function corresponds to the particle should be square integrable function. So after integrating its probability density, we should get a finite value. Otherwise, what is its meaning? The particle is extended from minus infinity to plus infinity. Then how we can call it as a particle? So psi must be a square integrable function. Third one, the psi must be continuous and single valued. That is, suppose this is a wave function which is not a continuous like this. The wave function corresponds to some particle. So what is the problem here? Here this is x-axis, right? So at this position of x, you can see the particle is jumping from this position to another position. That is, it is vanishing from here and it is appearing here suddenly. It's like a magician. But this is not possible for a particle. A particle can't disappear from certain position and appear in the another position. It is not possible. It have to travel the distance. Okay. So this kind of wave function is not possible. That is why we are telling the psi must be continuous function. And it should be single valued function. Here you see at same x value, that is some x equal to a, we get two wave functions, psi 2 and psi 1. So we get two probabilities. So we get two different probabilities for same position. That is also not valid condition. So the phi must be continuous and it must be a single valued function. Fourth one, dou phi by dou x must be continuous and single valued. That is, the wave function should be like this one, that is, it will change its slope smoothly. This is possible, and a wave function like sawtooth is not valid for representing a particle, because at this position you can see dou phi by dou x is suddenly changing, the slope is suddenly changing. Okay, see, these are the various wave functions, and now we have to check which of the following wave functions will be valid one. Now let us check one by one. So for the first one, at this position it have two phi value, that is, it is double valued. So this is not possible, because for a particular position it will have two psi values. And the second one, yeah, it is valid one, right? And third one, it is also valid one, because it is converging function. And for fourth one, you see, it is disappeared from here and it is appeared here, and also it have double valued. Here it is discontinuous and it is a double valued. So this is also not a valid wave function. Here you can see d phi by dx is not continuous. The variation in the slope is not smooth. So this is also not valid. Here this wave function psi is extended to infinity. So it will not converge. So this is also not a valid wave function. Here some wave functions are given and we have to check which of them are valid wave functions. So what is the condition for valid wave function? It should converge. The wave function should converge when x tends to plus or minus infinity. So if it is converging, then it is a valid. Okay, so we can check. First one, psi equal to sin x. If x tends to infinity, what will happen? Is sin x will converge to 0? No. So as x tends to infinity, what will happen? The wave function psi also tends to infinity. So it is not valid. Second one, x tends to infinity, what will happen? Yeah, cos x also, that is psi also tends to infinity. This is also not valid. And here what happened? X tends to infinity. Here also psi tends to infinity. And one more condition is there for the function of tan x. We can see there is a discontinuity. So it is also discontinuous function. So this is also not a valid wave function. And here what happened when x tends to plus or minus infinity? Yeah, wave function should tends to infinity, and this is also not valid. Yeah, for x tends to n also, this is not valid. Here when x tends to plus infinity, the wave function tends to infinity, and this is not valid. And if x tends to minus infinity, then the wave function tends to 0. So in the negative x-axis, this function is valid. And for this one, when x tends to plus infinity, psi tends to 0. So in that region it is valid, but when x tends to minus infinity, psi tends to infinity. So in the negative x region, this wave function is not valid. And for the first case and second case, I am adding some more conditions. Suppose the region is specified, that is sin x for a limited region, then this will be valid because the function is continuous and the value will be finite value. Okay, and for cos also, for a region it is finite and it will converge. So within a boundary it is valid. But in general it is not a valid wave function. So if you are taking a particle in a box, then we can use sine wave function and the cos wave function because it is bounded. Okay, the particle is moving in a boundary only. But in general we cannot use psi equal to sin x or cos x as valid wave function. Normalization. What is this process? We can represent a particle in quantum mechanics as a wave packet. See, this is a wave packet representing the particle. Suppose I am extending this axis to plus infinity and this axis to minus infinity. So a particle in a classical mechanics is represented by a wave packet in quantum mechanics. So anywhere in between this distance, that is delta x, uncertainty in position, we can find the particle. Okay, and for the particle to appear here, it will have a certain probability, and for the particle to be found here, it will have a certain probability. So the probability is distributed in the delta x distance. Okay, that is the probability is phi star, that is nothing but mod psi square. Now I am going to look for the particle from minus infinity to plus infinity. Okay, so definitely I can find the particle in between minus infinity and the plus infinity. So the probability of finding the particle, if I am looking from minus infinity to plus infinity, is 1, right? And if I am looking only this region from here to plus infinity, then what is the probability of finding the particle? Only half, right? And if I am looking from this location to this to infinity, then what will be the probability of finding the particle? That will be equal to 1 by 4. So if you are looking for a particle from minus infinity to plus infinity distance, then the probability of finding the particle will be 1, because in between minus infinity to plus infinity, particle will be there. Okay, that is probability of finding particle from minus infinity to plus infinity is 1. So I can represent this idea in a mathematical way, that is integral minus infinity to plus infinity mod psi square dx is equal to 1. So if I am integrating this probability from minus infinity to plus infinity, what I get? You will get 1, right? And this is the condition for normalization. Suppose, for example, if we are integrating a wave function from minus infinity to plus infinity mod psi square dx, that is minus infinity to plus infinity psi star psi dx. So suppose we got the value as 2. So what is the problem? The problem is, if it is 2 or some other value, then this wave function is not physically representing the particle. So what we have to do? We can do the normalization. What is it? We have to make this value equal to 1. So what we do? We have to make the right hand side 1. So we have to divide with both sides with half. So minus infinity to infinity psi star psi dx is equal to 1 by 2 into 2. So now right hand side become 1. So Now I want to modify our wave function in order to represent the physics of the particle. That is what we can do. We can take minus infinity to infinity 1 by root 2 of psi star into 1 by root 2 of psi dx. So what we get? We get 1. So making the wave function in order to represent the particle, that process is called normalization. So now we normalize the wave function, that is 1 by root 2 psi. So now this wave function can represent the physical reality of the particle. Okay, and that process is called normalization. Some important formula for solving the normalization problem. First formula, integral minus infinity to infinity e raised to minus ax square into dx will be equal to root pi by a. Second formula, integral minus infinity to infinity e raised to minus ax square plus bx plus c will be equal to root pi by a e raised to b square minus 4ac by 4a. See, second one is extension of the first one, right? Third one, integral 0 to infinity x raised to n e raised to minus ax dx will be equal to n factorial by a raised to n plus 1. And fourth one, integral x1 to x2 sine square x dx will be equal to x1 to x2 cos square x dx, and we get the value as 1 by 2 into x2 minus x1. So where x2 minus x1 is the interval of the integration, and this formula is valid only for full and half intervals only. Okay, I'll tell you what is this full and half intervals. Okay, don't worry. These equations are very, very important. If you know this equation, then you can solve this problem very easily. Example problems. First example, wave function psi is equal to a sine n pi x by L. The question is to normalize the wave function. So how to do? We have to take the integral, that is psi star psi dx. Now here I am telling this limit, that is limit is between 0 to L. So the integral should be from 0 to L, where L is the length of a 1D box. Okay, so we have to find out the normalized wave function inside a box of length L. Okay, so for wave function to represent a particle, then this value should be equal to 1. So that is 0 to L psi star. Conjugate of this function is this one itself, that is a sine n pi x by L into psi, that is a sine n pi x by L into dx. It should be equal to 1, right? That is, we get integral 0 to L a square into sine square n pi x by L into dx should be equal to 1. So we can take this a square outside. So integral 0 to L sine square n pi x by L dx. Just before I told you a formula to find out integral of sine square x. What is that? That is a square into 1 by 2 of the limit. Here the limit is 0 to L. That is 1 by 2 into L. And this value should be equal to 1. So we can find out that a square is equal to 2 by L. So a must be equal to root of 2 by L. So what will be the normalized wave function? The normalized wave function will be psi is equal to a equal to root 2 by L into sine n pi x by L. So this wave function can represent the particle in a box. That is the meaning of normalized wave function. That is that mathematical representation is valid for its physical reality. Another example, psi is equal to a e raised to minus half alpha square x square. Normalize this wave function. That is, you have to find out minus infinity to infinity mod psi square dx equal to 1. That is minus infinity to infinity mod psi square, that is psi star. So what we get? A square e raised to minus alpha square x square dx. That is equal to a square into integral minus infinity to infinity e raised to minus alpha square x square dx. Now see, we can use the formula. So what we get? We get a square into root pi by a. Here in the position of a, it is alpha square. Okay, and that will be equal to 1. That is a square root pi by alpha should be equal to 1. So we can find out this a square value. That is a square is equal to alpha by root pi. So what should be the a value? A value should be root of alpha by root pi. So what is the normalized wave function? The normalized wave function will be root of alpha by root pi e raised to minus half alpha square x square. Now this wave function is valid for representing a physical particle. Okay. Another example, wave function psi is equal to a e raised to minus r by a0. This wave function represents the electron cloud. This electron cloud has a spherical symmetry. So we have to integrate over the volume element, and that is dv element, right? And phi is represented as a function of r. So this is a spherical polar coordinate system, or this electron cloud has a spherical symmetry. So we use spherical polar coordinate system r theta phi. So in spherical polar coordinate system, the volume element dv is equal to r square dr sine theta d theta d phi. And I think you know the limits. The theta will varies from 0 to pi, and phi will varies from 0 to pi. Okay, and in the question it is given the r value is in between 0 and infinity. Okay, now what is the condition for normalization? That is integral psi star psi dv, because now we have to integrate over this entire volume. Okay, and we know what is this dv. Dv is equal to r square dr sin theta d theta d phi. So we can substitute all these values. So what we get? We get a square e raised to minus 2r by a0 into r square dr sin theta d theta d phi. So we have to integrate this d phi from 0 to 2 pi, and sin theta d theta from 0 to pi, and r value from 0 to infinity. And I think you know what is this value of integral over d theta? It will be 2 pi, and integral over sin theta d theta will give a value of 2, and the remaining part is this one only, that is 4 pi a square integral 0 to infinity into r square e raised to minus 2r by a0 dr. And I told you a formula for solving this kind of problems, that is integral 0 to infinity x raised to n e raised to minus ax dx will be equal to n factorial by a raised to n plus 1. So here in this problem n is equal to 2, right, and a is equal to 2 by a0. Okay, so now we can use this equation, that is we get 4 pi a square into n factorial, that is 2 by a raised to n plus 1, that is 2 by a0 raised to 3, and we have to equate this to 1, right? So now we can find out the value for a square. Please find out it. It's a work for you. Probability. Let us consider a particle is moving inside a 1D box. So 1D box of length 0 to L. So when a particle is moving in this box, it will become a wave. Suppose this is the corresponding wave for this particle. Then here the question is to find out the probability of finding the particle at various intervals. If we want to find the probability from A to B, this is the interval between A and B. Then the equation for probability will be integral A to B mod psi square dx. And for this 1D box, the corresponding wave function psi is equal to root 2 by L sin pi x by L. Now my first question is, you have to find out the probability to find out the particle from 0 to L distance. So that is equal to integral 0 to L mod psi square, that is 2 by L sin square pi x by L into dx. That is equal to 2 by L into, I told you a trick to solve the integral of sin square x, that is 1 by 2 into the interval. So here interval is L. So what we get? We get 1. See, this one is physically also true. For this particle, if this is the wave function, in between 0 and L, you can definitely find out the particle, right? So the probability of the finding particle between 0 and L is definitely 1. Now, what will be the probability to find out the particle from 0 to L by 2? So up to this distance, half. What will be the probability? So what is the equation? This is equal to integral 0 to L by 2 into mod psi square, that is 2 by L sin square pi x by L dx. So what we get? We get 2 by L into the trick, that is 1 by 2 into the interval. Here the interval is 0 to L by 2. See, that is L by 2. So what we get? We get this is equal to 1 by 2. Third one, find the probability to find the particle in the region 0 to L by 4. So what you have to do? You have to integrate, that is from 0 to L by 4 to by L sin square pi x by L dx, and find out the answer. This is a work for you. I tell you the final result. The final result will be 1 by 4 minus 1 by 2 pi. You please solve this problem. Okay, it's a work for you. Here we can use the tricky method for sin square x. Why? Because when I am telling this trick, I told you it is valid only for full interval and the half interval. Here it is quarter interval, 0 to L by 4. So we can't directly use that trick. Here we can rewrite this sin square pi x by L as 1 by 2 into 1 minus cos 2 pi x by L. Then substitute this value in the position of sine square pi x by L and do the integration. You get the result. Fourth one, find the probability to find the particle in the region L by 4 to L by 2. This is also a work for you. Just solve this equation and finally you will get this answer, that is 1 by 4 plus 1 by 2 pi. That is for a 1D box of length 0 to L. This will be the ground state wave function. For this region, the probability of finding the particle in this region will be 1 by 2 and this region is also 1 by 2. And find this particle in this region will be equal to 1 by 4 minus 1 by 2 pi. That is, this is L by 4, this is L by 2 and this is 3L by 4. And you get the probability to find out the particle in this region as 1 by 4 plus 1 by 2 pi. See, these are very important, okay? Here these are the graph corresponds to option A, option B, option C and option D. Here the question is to find out a possible solution of Schrodinger equation for a particle, right? So for the first option, the particle can be a bounded particle, so it can oscillate in between these two boundaries, right? And what is the problem in option B? Here, when particle is at position x equal to 0, then it will have, the wave function will have value infinity. That is not a possible one. That is, wave function is not definite. So this is not a possible. Here in the option C, what is the problem? When particle is at x equal to 0, it will have a definite wave function, and when the particle is at a distance little bit far away from x, then also it will have a definite wave function value phi. But when particle is at this x position, the wave function value will be infinity. So this one also not a possible wave function. And option D, it is a tan function, and you know, for a tan function, when particle is at this position, wave function size definite, but when the particle is at this position, the wave function value will be infinity. So this is also not a possible solution for a particle. This question is about physical meaning of normalization. What is the normalization condition? We know the normalization condition is integral minus infinity to infinity mod psi square dx should be equal to 1. What is its meaning? That is, if you are integrating some function from minus infinite value to plus infinity, the wave function should be finite. That is, area under the curve should be a finite value. So some functions like discontinuous functions are not possible, okay, and if some function is going to infinity, then also it is not possible. So only for those functions, if you are integrating from minus infinity to plus infinity, we should get 1. Such functions only we can use in quantum mechanics to represent the particles. So the option D is the correct answer. The wave function is finite everywhere. This one is a previous gate question, and the question, which of the following is allowed wave function for a particle in a bound state? So the question is about wave function of a particle and it is in a bound state. What is that meaning? That is, you know, particle is a localized one. So a particle will not extend from minus infinity to infinity. The particle will be at a certain position only. And here it is specified, that is, it is in a bound state. That means it is like a particle is moving in a box. So the wave function also will be bounded to a certain region only. That is, it will not be extended to infinity. Okay, so now we can check each of these options. So first option is psi is equal to n e raised to minus alpha r by r cube. Here this wave function have certain spherical symmetry because we know r vector is xi plus yj plus zk. So it has a certain spherical symmetry, right? So the r value will varies from 0 to infinity. So we can check what is the value of the psi when r equal to 0. What will be this value? The psi value will be equal to infinity. Why? Because 1 by r cube is there. When r is 0, then 1 by 0. That is definitely infinity. Okay. And when r tends to infinity, then the wave function will tends to 0. So this wave function will look like this one. See, when r is equal to 0, it is giving infinite value. So when we are integrating this function, we get infinite probability. That is, this is non-integrable function. So this is not a allowed wave function. Now we can check the second option. That is, psi is equal to n into 1 minus e raised to minus alpha r. Again, we have to check what is the wave function psi when r equal to 0. When r equal to 0, the psi value will be equal to 0. And when r tends to infinity, the psi value tends to n. That is, this wave function look like this one. That means this wave function is extending to infinity with a constant value. So this wave function also can represent the bound particle. Now we can check the option C. That is, psi is equal to n e raised to minus alpha x e raised to minus beta x square plus y square plus z square. That is nothing but r square, right? So now we can check. If r equal to 0, definitely x value also will be equal to 0. Then what will be the psi value? The psi value will be equal to n, right? And when r tends to infinity, then x also tends to infinity. Then what will be the psi value? Psi value will tends to 0. So when we are plotting this function, you get a function like this one. See, this is a localized one, right? It is bounded to a certain region. So this is the correct answer. This is the corresponding graph for the given option A, and this is for option B, this is for option C, and this is for option D. So among this one, you can find out option C is representing the bound particle. Why? Because in the option C, the wave function is localized to certain region only. So it can represent the particle in bound state.